Dear students, welcome to our science episode. Today we are going to continue discussing wave motion. We know from the previous episodes that periodic motion is regularly repeated in equal periods of time. And oscillatory motion is an example. The second example is the wave motion. Think what will happen if you will touch the surface of a still water. A horizontal disturbance will make propagation of concentric circles on the surface of water, representing a wave motion. Here is the wave motion. You will disturb the surface of the still water, making propagations of concentric circles. This is called wave motion. Wave motion is a form of periodic motion. Here is an activity to represent the role of wave in energy transfer. We will place some pieces of dominoes in a line and make sure the pieces are placed at equal distances from each other. Push the first domino piece down. You will find that when the first domino piece falls, all the domino pieces will fall one after another. The first domino piece will transfer its energy to the next piece, and so on. Energy transfer through the domino pieces continues, and the pieces never change position in the line. As a conclusion, the disturbance that propagates and transfers energy in the direction of propagation is known as a wave. Look at these pictures and explain the motion of the coin Y when the coin X is pushed, though they never touch. Here is the coin X and here is the coin Y, and you will explain the motion of the coin Y when coin X will be moved toward these stack of coins. Look at picture B. You will find that the coin Y will move when the coin X will be pushed, because the coin X will transfer the energy to the piece after, and so on until the energy is transferred to Y and the coin Y moves. Now look at this activity and let us discuss it together. We're going to get a hollow tube 30 centimeters long, a burning scene stick, a candle, and a tuning fork. We're going to place the tube horizontally. We're going to place the candle at one of its ends and the scene stick at the other end. Hit the tuning fork and place it near the scene stick. We will find that the tuning fork vibrates, producing energy, and these energy will be transferred as sound waves. The air and the smoke particles do not move from their original places, but these sound waves will carry energy to the candle flame. If you look at this, we are going to hit the tuning fork. The tuning fork will produce sound waves. These sound waves will carry energy and through the glass tube to the candle. The flame of the candle will move accordingly. So the movement from the vibration of the medium particles in a specific direction is a wave motion. The direction of wave progression is known as the line of wave propagation. So, if this is the source of the sound waves will cause vibration of the medium particles, let's say the air particles, and propagate in the direction of the wave motion in a line called a line of wave propagation. So why do waves cause erosion of coastal areas? Let's see together. Water waves transfer energy as they hit the shore, causing erosion. Waves are classified according to the direction of vibration of medium particles relative to the direction of propagation into transverse waves or longitudinal waves. Waves are also classified according to the ability to propagate and transfer energy into mechanical waves or electromagnetic waves. Now we are going to compare between transverse and longitudinal waves. Get a spring, a colored ribbon, and a nail. Fix the end of the spring to the wall using a nail. And tie the colored ribbon at the middle of the spring. Move the spring coil up and down. Push and pull the coil at the free end. If you will move the coils of the spring up and down, this is the direction of the vibration, while this will be the direction of the wave propagation. The spring coils will move up and down, forming crests and troughs. This is called transverse waves. While if we are going to push and pull the spring coils will move in the direction of the vibration, forming areas of rarefaction and areas of compression. Notice that the compression areas, the coils are near to each other, while in rarefaction areas, the coils are away from each other. And these are called longitudinal waves. Now let me show you the two types of waves. If you will hold a spring and then you will move it up and down, then the waves will do crests and troughs. Okay, this is called transverse waves. The propagation is in this direction. This is transverse waves. But in the longitudinal, you're going to push and pull, forming areas of compression and then areas of rarefaction. Compression and rarefaction. And these are called longitudinal waves. During wave propagation, the particles of the medium do not change position. However, they vibrate around their point of rest. Let's now compare transverse and longitudinal waves. Transverse waves is a disturbance causing particles of the medium to vibrate perpendicular to the direction of the wave propagation. Remember that we are moving the spring or the rope up and down. This is the direction of movement. But the waves are propagating in this direction. This is the direction of propagation. So the movement and the propagation are perpendicular to each other. The crest here is the highest point of the wave, and the trough is the lowest point of the wave. In longitudinal waves, the disturbance and the line of propagation are in the same direction. They are parallel to each other. So look at this picture. We are pushing and pulling the spring. So this is the line of movement or vibration. And at the same time, this is the direction of the wave propagation. Both are in the same direction, or we can say that they are parallel to each other. So in transverse waves, the movement and the wave propagation line are perpendicular to each other, while here the movement line and the line of propagation are in the same direction or parallel to each other. These are the longitudinal waves. Remember, in the longitudinal waves, we are making an areas of compression where the particles of the medium are too close to each other, and another areas of rarefaction where the particles of the medium are away from each other. This is a transverse wave. The movement is perpendicular to the wave propagation line, making crests and troughs. Here is the longitudinal wave. The movement is parallel to the direction of the wave propagation and forming areas of compression and areas of rarefaction. The trough in the transverse wave are equal to the area of rarefaction, and the crest in the transverse wave is equal to the or represented by the areas of compression in a longitudinal wave. Did you see the jacuzzi before? This is a real-life application for waves. Let's see together. In most health clubs, you can find physiotherapy tubs called jacuzzi. In a jacuzzi tub, water moves in circular waves, and they are used to treat sprains and cramps with hot water and nervous tension when used with cold water. Now it's time for questions. Write the scientific term, the disturbance that propagates and transfers energy in the direction of propagation, waves. The highest point in a transverse wave with respect to the horizontal line of rest, its crest. A disturbance causing particles of the medium to vibrate perpendicular to the direction of wave propagation. Transverse waves. A disturbance causing particles of the medium to vibrate in the same direction of wave propagation. Longitudinal waves. Thank you. Dear students, thank you for watching. See you later in other science episodes.